Hello, we're Team Dot from Russia, St. Petersburg. We're participating in RoboCup Asai-Pacific 2021 in Soccer Open League. In this league, robots play soccer with an orange ball on special field, according to the rules similar human soccer. The match is divided into two parts of 10 minutes each. The team that scores the most goals wins.
Our team has been participating in robotic soccer competitions for almost 4 years. Working for such a long time, we had to solve a lot of complicated problems. One of the hardest of them was lack of debugging time. This year, we tried to avoid this problem using better time management and efficient planning.
As there weren't any changes in the rules from the last year, our robot's hardware part had only some tiny modifications. However, we made several significant improvements in its software part. Now we are ready to provide you more information about its development process. At first glance, our new robots look exactly like all other. But this time we made several significant improvements that really differ our new construction. First of all, this year we began to use Maxon brushless motors instead of brushed Polalo. And to use them properly, I made special OmniWheels modules. Each of these modules consists of bearing hub, built-in gearbox with a gear ratio 3:1, OmniWheel itself, motor mount and motor. Such construction minimizes all radial loads on the motor shaft, and also it allowed us to make all wheels exactly the size that we need to. Another one great feature of our 2020 robot design are two dribbles placed on opposite sides of the robot. We decided to use two of them to spend less time approaching ball from every angle. My dribble design uses two separated rollers. I found that this configuration works better on higher angular velocities. To kick ball from both dribblers, our robot used advanced kicker system. I made it in such a way that robot can kick ball in 3 different directions from each dribbler using only 2 solenoids. As well, we put lots of useful electronics and various sensors in our robot. For example, here we have one board computer header swim 3, brain of our robot. Or here is LiDAR sensor. We use it to clarify our own position on the field or to detect enemies' robots. But still, the hardest challenge for me was to put all required hardware into the body that would compile with 2021 rules. Thus, robot diameter is only 197 mm and its weight is under 2300 grams.
Electronics is a very important part of each robot, so there are a main and 7 additional self-developed boards in our new robots. The main boards group include the motherboard, the line sensor board and the boost voltage regulator. The additional boards group include 4 ball sensors, the battery board and 2 communication boards for camera and LiDAR sensor. In the developing stage of our new robot, we had faced some problems. At first, we began to use smaller solenoids than last year. To keep the kick force, it needed to charge the capacitors with a high voltage. To do this, I had to develop a boost voltage regulator that would be able to charge capacitors up to 250 volts. Because of another problem, I made a new line sensors board. Our old robots often went out because they didn't see the line well. I solved this problem by changing the line sensors to other with bigger viewing angle. Furthermore, I placed them in the form of a cycle instead of a cross. Now, our robots always see the line perfectly.
Our robot detects ball and goals by color using my own developed color space approximation algorithm. It helps to determine the position of the ball and goals on the field with higher accuracy. Our code split it into 2 parts. First part runs on STM32 and controls the velocities of the motors. Also, it obtains data from sensors. Second part runs on single board computer Vim and it detects the position of the robot and ball on the field and calculates it with very high accuracy using some advanced techniques such as noise amplitude estimation and trajectory prediction. Now we will show you our robots in play. We made a lot of strategies, and the best of them is the one presented. The attacker rotates and moves directly to the ball, while it's not in the dribbler. Then, robot moves to the closest out area as fast as possible to avoid any collisions with enemy robots. It rotates so the ball will not be seen by the enemy's goalie, moves to one of the several good striking positions, and swiftly rotates and kicks the ball to the goals. It is now impossible for the enemies to block such strike. If the ball is in the same direction as the enemy goals relative to the attacker, robot accelerates and strikes the ball with dribbler instantly. The goalie predicts the trajectory of the ball, intersects it with the goal outline, and moves to the intersection. If the ball is close, goalie is trying to kick it using small quick movements towards the ball.
Summarizing our work on this project, we can definitely say that these robots are the most technologically advanced and reliable of all that we have ever made. But such a complexity took a lot of time and resulted in huge robot costs. Looking forward to another projects like this, we'll try to find better balance between complexity and practical efficiency of our designs. Hope you found this video interesting and learned something new. Goodbye.